Hi, everyone. So this week we have Sophia Elia from Berlin, who will be talking about congruence normality of simplicial hyperplane arrangements.
Hi, everybody. Thanks for coming, and I'm really excited to talk to you today. I'm going to be telling you about some joint work I did with Michael Kuntz and Jean-Philippe Lebet. And what we did was we looked at simplicial hyperplane arrangements and studied whether they, in particular their posets, have a certain property called congruence normality. So in the first part of the talk, I want to give some background and tell you about what these different terms are. And then I'll tell you how we went about testing whether the arrangements have this property. And then I'll tell you what we found. So let's start off with some definitions. So we're in a real vector space, d-dimensional vector space. And a hyperplane in this space is just going to be a codimension 1 subspace. So we can define it by taking our favorite vector and then looking at the set of points that are orthogonal to that vector given the usual dot product. So that's a real central hyperplane. It's central because it contains the origin. And a hyperplane arrangement is then a finite non-empty set of hyperplanes. So we also want to talk about the regions of the arrangement. So if we look at the complement of the arrangements in our space, then this partitions the space into a bunch of different connected components. And the closures of those different connected components are the regions of the arrangement. A region is going to be called simplicial if each of the normal vectors to its facet defining or bounding hyperplanes are linearly independent. So the entire arrangement will be simplicial if every region is simplicial. And finally, these are a lot of definitions in a row, but the rank of the arrangement is the dimension of the linear span of all of the normals to the hyperplanes. So are there any questions about that? Oh yeah, okay, so in the rank 3 case, so now we're in a 3-dimensional vector space and we're looking at 2-dimensional planes that all contain the origin. There are some things known about these arrangements. So in particular, we can draw them as lines in the plane. And the way that we do this is we just choose a hyperplane, which is not parallel to any of the hyperplanes in our arrangement, and we intersect. And in this way, we can view the arrangement as lines in the plane, like the arrangements that you see here. So in 1971, Grunbaum published a first catalog of these simplicial arrangements and drew many pictures of them in the projective plane. In particular, there were 3 infinite families and then some sporadic exceptional examples. So the 3 infinite families are what you see here. The first family is the family of near pencils. And in these arrangements, all of the hyperplanes, which we're seeing as lines, contain a common intersection point, except for one. And then you can see that each of the regions in this arrangement is a triangle. That's what makes it simplicial. So the second family comes from polygons, regular polygons, and their lines of symmetry. So here we have a regular pentagon, and we have each of its 5 lines of symmetry, and the hyperplanes coming from the affine spans of the edges. So that's the second infinite family. You have one of these arrangements for every n-gon. And then the last family comes from the even n-gons, where you again take hyperplanes coming from the edges and the lines of symmetry, and then you add in the hyperplane at infinity. So these are the infinite families of arrangements. But then interestingly, there are these exceptional examples. So Grunbaum also found 90 sporadic exceptional arrangements. And the number of hyperplanes in these arrangements ranges from 7 to 37 hyperplanes. I've just selected 6 of the arrangements from his paper, but it's a really beautiful paper if you've never looked at it before. There are all of these great drawings. So at the time, Grunbaum conjectured that this list, his catalog, was actually complete. But there's a lot that remains. I mean, it was just a conjecture, and also there was a lot of open questions about it, like where do these arrangements come from, and is 37 a real upper bound for the number of hyperplanes in one of these simplicial arrangements?
Can I ask a question?
Yeah, sure.
This classification is up to what? Like the homothétie, or like what is allowed here?
Right. So it's actually not clearly stated in the paper because it's sort of a tricky question. But mostly you can think of projective equivalence. Sometimes the right notion is like isomorphism of the oriented matroid. And the reason that that's a difficult question to answer is that if you want to use projective equivalence, then like you can see that for the near pencils, 2 different near pencils with the same number of hyperplanes should be equivalent, but they're not projectively equivalent.
I see. So
mostly it's projective equivalence, but we also test things up to isomorphism of the oriented matroid. Does that answer your question?
Yes, thank you.
Okay.
Excuse me. Did you say that they are not projectively equivalent?
For the near pencil case.
Okay.
Right.
Thanks.
Okay. So since 2009, there have been a few changes to the catalog of these rank 3 simplicial arrangements. 5 new sporadic arrangements have been found. 4 of them were found in 2011 by Michael Kuntz, and then an additional arrangement with 35 hyperplanes was found earlier this year. In the 2011 paper, Kuntz also showed that the list is complete for arrangements with up to 27 hyperplanes. But it's still not known whether all of the sporadic arrangements have been found, or in fact, even if it's should be a finite number, or if 37 is a true upper bound for the number of hyperplanes. So there's a lot that's still unknown. As for like structural information, it's been found that about half of the sporadic arrangements come from finite Weyl groupoids. So these are generalizations of Weyl groups, if you've heard of that before. And they correspond to crystallographic arrangements. So there's some structure that has been found behind about half of these sporadic arrangements. But you can see that there's still a lot to discover about the catalog. So one of the things that we did in this article was provide normals and invariants of all of the known simplicial hyperplane arrangements in rank 3. So if you actually want to get your hands on these arrangements and play with them, you can do that. And then the other thing that we wanted to do was add some more structure to this catalog. So what we decided to do was test whether each of the arrangements has this property called congruence normality, which I'll tell you about next. Okay. So this is actually a property of a poset associated to the hyperplane arrangement. And the way that we create the poset goes like this. we choose one of the regions of the arrangement and we orient all the normals away from that region, which is a property that you can test using the dot product. So then the separating set of a region, we're going to assign a set of hyperplanes to every region of the arrangement. And a hyperplane will be in the separating set of a region if that hyperplane separates that region from the base region. So if they're on opposite sides of that hyperplane, which is again something that you can test using the dot product. So then we create a partially ordered set called the post set of regions, whose elements are regions of the arrangement. And we have that one region is less than or equal to another if and only if there's a containment of the separating sets. Oh, sorry. Okay, great, so let's look at an example. Okay, so this is an arrangement of 3 hyperplanes in 3-dimensional space, and I've labeled the different regions of the arrangement. I've chosen this to be the base region, and then I've just labeled the other ones. So for the post set of regions, the base region just has an empty set, so it's the lowest element in our post set. And then to go to, for example, region 2, I have to cross the red hyperplane. That means that the separating set of region 2 is going to contain like the red hyperplane. And then to go to region 4, I have to cross from the base region, I have to cross both the red hyperplane and the green hyperplane. So region 4 is going to have separating set red and green, and there's a containment there. So I get an edge in my post set or a Hasse diagram. Is that clear enough? Okay. So this isn't the only way that you can get a post set from a hyperplane arrangement. In fact, Aram has a paper studying the facial weak order. And this is like the post set of regions is a sub-post set of the facial weak order. And there are some nice relations there. And then there's another post sets associated to a hyperplane arrangement, which is the intersection lattice, whose elements are different intersections of subsets of the hyperplanes in our arrangement. So the one that we're looking at today, though, is the post set of regions. And what we know about this post set is that if your arrangement is simplicial, then the post set of regions is going to be a lattice for any choice of base region. And more than that, getting to the property that we want to look at today, congruence normality, for a subset of these simplicial arrangements, the arrangements that come from Coxeter arrangements, we actually know that the post sets of regions are always congruence normal. So it's a nice question to ask, okay, we have a nice subfamily of the simplicial arrangements that have congruence normal post sets of regions. Which other ones have this property? So let me tell you what congruence normality means. A subset of a post set is convex if for any 2 elements in the post set, we have the entire interval between those 2 elements. So a lattice is congruence normal if there's a finite sequence of doublings of convex sets that so that you can obtain the lattice from the 1 element lattice. So let's look at an example of this. So if I have the following lattice, 4-element lattice, let me just label the elements, 1, 2, 3, 4. So the way that I would double create a doubling of a convex set within this lattice is, first of all, I need to choose a subset, a convex subset. So in this case, I'm going to choose the elements 2 and 3. Let me choose a different color, sorry. 2 and 3. This is my subset. And now what I do is I'm going to create 2 distinct copies of this subset. So I'm going to create one copy at height 0 and one copy at height 1. So this one will be my copy at height 0, and this one will be my copy at height 1. And then in the top copy, I'm going to include like the order filter of this subset. So all of the elements in my post set that are above the elements 2 and 3. So I get 4 also at height 1. And then I look at the complement of that filter and put that at height 0. So I get 1, 0. And now the relations here are that one element is less than or equal to another if we have that relation in both coordinates. So in this way, you can see that a hexagonal lattice is one of these congruence normal lattices. And what it corresponds to is that you have a way to construct in terms of the hyperplane arrangement, what it means is that you can construct it by adding in hyperplanes one at a time. So there's a related notion called congruence uniformity, and it's stronger, but in the simplicial case, they're equivalent. And it's the same thing, but with intervals, doublings of intervals. Okay, so that's the notion of congruence normality. So the reason that it's natural to study congruence normality is that when a lattice is congruence uniform, or in the simplicial case, also congruence normal, it's easier to understand the lattice congruences. And the reason that you would want to do that, or one of the reasons you would want to do that, has to do with zonotopes. Anytime that you have a simplicial arrangement, it is the normal fan of a simple zonotope. So then when you start looking at lattice congruences, you get into really interesting topics and questions in combinatorics. You hit like the permutahedron and the issosahedron, and you can ask questions like, if I take a cone in my hyperplane arrangement and I like start gluing the cones together, do I still have the normal fan of a polytope? And this is a question which has been answered in some cases. It's been answered in type A in 2019 in a paper called Quotient Topes by Pilo and Santos. And in a paper earlier this year, in like July, Pilo, Ritter, and Pedrol showed that they conjectured that if your post set of regions is congruence uniform, then in fact, any of these quotients will be the normal fan of a polytope. So hopefully that can convince you that this is actually a property which crops up a lot and is interesting to study and to know which arrangements actually are congruence uniform or congruence normal. Okay, so far we talked a little bit about what's known about simplicial hyperplane arrangements in rank 3 and looked at some of the pictures from this catalog. And right now we're trying to figure out which ones are congruence normal. So lattice is congruence normal if it's obtainable through a finite sequence of doublings of convex sets. That's one way to look at it. And then we saw some motivation for looking at this property. It crops up when you start asking different questions about lattice quotients. And now I want to talk about how we can actually check if a simplicial hyperplane arrangement is congruence normal. So our starting point is going to be a geometric notion, way to check for congruence normality. using pieces of the hyperplanes called shards. So this was introduced by Nathan Reading in 2003. And I just want to walk you through how we get the shards of a simplicial hyperplane arrangement. So right away, you probably notice that this arrangement looks a little bit different than the arrangements that we saw before, because this arrangement has both circles and straight lines. And the reason for this is that this arrangement was drawn by taking all of these central planes, intersecting them with a sphere, and then doing a stereographic projection. So now instead of just straight lines, we have straight lines and circles. But you've actually seen this arrangement before. It's the arrangement that comes from the pentagon. And I've selected a base region. So the post set of regions is always dependent on which base region you choose. And here I've selected this one. So this hyperplane arrangement has 10 different hyperplanes. And it's actually a special one. It's the smallest simplicial, like according to number of hyperplanes, the smallest simplicial hyperplane arrangement, which has a choice of base region such that the post set is not congruence normal. So let's see this. So how we create the shards is we choose our base region, and then we have to look at every intersection point within the hyperplanes. So every place where at least 3 hyperplanes intersect. So for example, I can look at this intersection point. And then I sort of forget about all of the other hyperplanes. I'm looking at this subarrangement. And now I ask, okay, in this subarrangement, which region contains my old base region? In this case, it's this region here, which is bounded by the pink and the black hyperplanes. These are called the basic hyperplanes of this subarrangement. And then what I do is all of the other hyperplanes that contain that intersection point get cut into 2 pieces. So now I go around and I do this at every single intersection that has at least 3 different hyperplanes meeting there. And I cut all of the hyperplanes into pieces in the way that I just told you. So the closures of these different pieces are the shards of the arrangement. That's a little fast, and like very visual. So feel free to ask if you want me to say that again.
No, but I would like to see the visual of one shard. Like when you say closure, do you mean that the little cut allows you to pass on both sides of the hyperplane there?
So for example, this is a shard here.
Oh, the little pieces, okay.
Each little piece, right? So
not the region.
Not the region, no. Like they're pieces of the hyperplanes. So
okay, thank you.
So yeah, at the intersection point, what I do first, let me go back to this picture, is from hyperplane 6, for example, I'm going to delete this intersection point.
Yes.
And then hyperplane 6 is split into 2 different pieces, but I just want, for convenience, I'm just going to take the closure. Like I want my shards to be closed. But yeah, I just take the closure of this set. And it's affine span. Okay. Okay?
Yes.
Cool. Okay, right. So shards actually can be used to detect congruence normality. And the way that we do this is we create a directed graph on the shards, and the arrangement is going to be congruence normal if and only if this directed graph is acyclic. So the way that you get the edges in this graph, you have to check for 2 criterion. One shard, there's going to be an arrow from one shard to another if 2 properties are fulfilled. First of all, the the hyperplane containing one of the shards cuts the hyperplane of the other. So in the picture, if we look at this red shard and this green shard, the red hyperplane cuts the green hyperplane in the way that we just saw. And the second criterion is a dimensionality criterion. And we have to have that the dimension of intersection of the two shards is actually of codimension 2. So in the picture, it just means that the two pieces actually did intersect at a point. And you can see that in this example, there's a cycle in the shards. The red shard cuts the green shard, cuts the orange shard, cuts the blue shard, cuts the red shard. So this is a simplicial hyperplane arrangement, which is not congruence normal for this choice of base region. Okay. That's like a geometric starting point, but the way that we wanted to test these arrangements for congruence normality is actually from an oriented matroid perspective. And so what we're going to do is encode the shards as covectors, or like tuples of signs, and be able to check for these cycles in this graph. And the reason that we want to do that is that then we don't have to work with polyhedral objects. We don't have to calculate dimensions of intersections or compute posetsets of regions. So this is just the way that we decided would be nice to go about computing things in this problem. Okay, so we want to interpret shards as certain tuples of signs called covectors. If we have an ordered set of vectors, then a covector on this set is just going to be, it's just going to record the sign of the dot product of a given vector of your choice with each of the vectors in that set. And what we're going to use this, like our set of vectors is going to be the set of normal vectors to the hyperplanes in the arrangement. And this will end up recording a lot of geometric information about the arrangement. So for example, if we have a hyperplane and its normal vector, and then we take another vector, then the sign of n dot v tells us whether we're on, like if it's equal to 0, then it means that we're on this hyperplane. If it's negative, it means we're on the same side as the base region. If it's positive, it means we're on the opposite side. So just these sign patterns can tell us a lot of information. And then what we'll want to do is forget about some of the entries in these covectors. So a restricted covector just puts stars in some of the positions because we won't care about them. Okay, so let me tell you about how we go from a shard to a shard covector. And I'm going to do this through an example. So focus on, oh, weird, okay. Focus on this shard, theta. It's a piece of hyperplane 6. And its shard covector is written down here. Oops, yeah. So for example, we can read off this covector. It has a star in the second position. And the way that we get the stars is we look at our hyperplane and we see which of the hyperplanes cut our hyperplane. So for example, hyperplane 5 and hyperplane 1 cut hyperplane 6 right here. Hyperplane 4 and hyperplane 3 also cut hyperplane 6, but you'll notice that hyperplane 2 doesn't cut hyperplane 6. And this is going to mean that it gets a star. because points in this shard occur on both sides of that hyperplane. So we don't care about the sign pattern there. Likewise, there's a plus in entry 1. And so that should mean that we have to actually cross hyperplane 1 to get from the basic region to the shard, which you can see you have to do. To go from the base region to the shard, I have to cross through hyperplane 1. And then likewise for the rest of the entries. So we were able to show that you can uniquely encode the different shards of your arrangement as these covectors, restricted covectors, which we call shard covectors.
Is this bijection only for simplicial arrangements or for arbitrary central arrangements?
It's for simplicial arrangements, but I don't see any reason why it wouldn't work for other arrangement, just central arrangements.
All right, thanks.
Okay. Right, so now we want to be able to detect cycles in the shards using the covectors. So there are two different tools that we need to do that. The first is another covector that's going to be associated to a line. So if I have a point configuration, then a line covector is a covector on this point configuration, which is 0 exactly on the line. So here, for example, if I took the line which is spanned by 1, 5, and 6, I could have the line covector I would take the line and then I would choose a positive side. And then I would get the covector with zeros on 1, 5, and 6. 2 is going to be positive, 4 is positive, and 3 is negative. So this is a line covector. And the way this plays in with our hyperplane arrangement is that we take the normals to our arrangement and we can get a point configuration by intersecting the normals with a hyperplane. And then we have a point configuration in codimension 1 space. So that's going to show up. And then we also introduce an intersection operation on covectors, which is sort of recording when points are on opposite sides of a hyperplane. So if we want to intersect sets that are on opposite sides of hyperplanes, then we're forcing them to the intersection to actually lie on the hyperplane. So it's defined coordinate-wise, and we have stars sort of acting as identities. If like stars, we don't really care about what the entry in that covector is. So a star intersected with anything is just that thing again. 0 intersected with anything is always 0. And then when you intersect a plus and a minus, you have to get 0 out. So then we showed that there's a directed arrow in the graph on shards if and only if the second shard covector has a plus or a minus in the appropriate coordinate. And this is recording that condition of one hyperplane cutting the other hyperplane. And then the dimensionality criterion is caught by this line covector condition. And it says that there has to exist a line covector such that if we intersect it with the corresponding shard covectors, we get the line covector back out. So now what's nice about this is we've translated this geometric criterion for checking for arrows in the directed graph on shards to just comparing two covectors coordinate-wise and really checking if they have a certain entry in a coordinate and then doing this intersection operation. Okay. So now I want to talk a little bit about what we found. So this is the newest found simplicial hyperplane arrangement that Kuntz found earlier this year. It has, well, it's zoomed in, but it has 35 hyperplanes, and you can see it's sort of has a something going on with the pentagon. It's pretty cool. So we found that the catalog broke into 3 different categories. Those posets of regions that were always congruence normal, no matter which base region you chose. Those posets of regions which were sometimes congruence normal. So there was a choice of base region where you would get a congruence normal poset and a choice where you wouldn't. And then posets that were never congruence normal. And in particular, there were these 5 sort of interesting, exceptional arrangements that I'll talk a little bit more about. But let's look at each of the categories. So in the always congruence normal case, we found that near pencils are always congruence normal. This is pretty easy to see because there's only one subarrangement where at least 3 hyperplanes intersect. So that means that any path in your directed graph on Shards is going to have at most 2 elements, length 1. There can't be a cycle. And then we found that simplicial arrangements from Weyl groupoids, actually, we were able to prove this in more generality of any rank, are always congruence normal. And we showed this by looking, by using the fact that Weyl groupoids, their roots actually form a poset, which turns out to block this cycle from happening. And then interestingly, there are exactly, besides the finite Weyl groupoids, there are exactly 2 other congruence normal arrangements coming from the Coxeter arrangement H3 and its point line dual. And so I think it would be an interest, if you wanted to prove that the list was in some way complete, it might be like, this is an interesting place to start thinking about. Is always congruence normal, like, are these all of the simplicial arrangements that are always congruence normal? I don't know, but I think it's cool. So then there was the sometimes congruence normal hyperplane arrangements. And these hyperplane arrangements included the infinite families coming from the regular polygons and their lines of symmetry. As soon as you had at least 10 hyperplanes in the second family and 17 hyperplanes in the third family. And then there were 41 other sporadic arrangements that are sometimes congruence normal. And these arrangements, they're fairly exceptional, and like, I think there's not that much known about them. And what's interesting is that, yeah, you can choose for some choices of base region, you get this. Remember that congruence normality means that we have a finite sequence of doublings of convex sets, so we can add in hyperplanes 1 by 1. And in these cases, that sometimes works, and then like that ordering of adding hyperplanes sometimes works and sometimes doesn't. So,
sorry, can you give us a sense of for what base region do we get congruence normal in those sometime congruence normal?
Yeah. So for example, in this arrangement, any of these regions will give you a congruence normal poset, and these ones won't.
And the one touching the infinity won't either? The unbounded one.
Yeah.
Can you do it?
I think it does, actually.
Oh, I see.
Because I can't remember for certain, but I think it is. I think these regions do give you congruence normal cosets.
So maybe by duality, we're sending 0 to infinity and infinity to 0, you get a similar problem. So only the region not touching either 0 or the infinity are good or bad. I don't know. And what about the other family? Same kind of phenomenon?
Same kind of story there, yeah.
But in the second family, all the region either touch 0 or infinity.
Right.
So which one are good or which one are bad?
So in the third family, you mean?
Yeah. That one.
So in the third family, well, there's a picture that we have in the article, but when you, I'm struggling to think. I'm struggling.
I'm sorry.
But it's your cycles do end up involving the hyperplane at infinity for this family.
Oh, so then just the one that touch that are close here are good, and all these are bad.
I can't quite remember, but I think so. I think so.
We can look at it again in the end.
Yeah. Okay. So right. So we're almost at the end, anyways. Then this last category of these three arrangements that are never congruence normal, which they have 22, 25, and 35 hyperplanes. And yeah, sort of like we were just talking about, this means that they're not constructible in some way. They're like appearing. And for example, this last one with 35 hyperplanes, this was found in Kuntz's paper from earlier this year. And what he did there was he created a greedy algorithm to find simplicial arrangements. And it quickly recovered all of the known simplicial arrangements in rank 3, and then found this one more. Yeah. So that's all that I wanted to tell you about. Thanks for listening.
Yay.
All right, let's thank the speaker. Are there any questions?
Well,
so
yes.
one question, well, other than non-tells, but one question I did have, so you had mentioned that for the always case, you don't necessarily know if that's a full list. Do you know that for any of the other two cases, whether for the almost or sometimes congruence normal or the never congruence normal, whether that's a complete
that list
list
is complete,
or whether they're not complete?
So what is known is that so most of the arrangements in the always case, they're coming from these finite Weyl groupoids, right? And finite Weyl groupoids are completely classified. So there are no more of those. And then this is like H3 and it's dual. And another interesting property is that H3 does admit like a root poset. So a guess here could be like, can you prove that these are the only simplicial arrangements with root posets or something like that? In the sometimes case, no, I don't think that there's really, yeah, in the other two cases, it's just not, I wouldn't have any idea about proving that those are complete.
For the second type of arrangements, and I guess the third, so here you have that for the second type, it's always congruence normal for less than or equal to 8, and then sometimes when it's greater than or equal to 10. How about when there's 9 hyperplanes? And then similarly for the third infinite family, because there's I guess 14 to 16 you don't have here.
Oh yeah, so this is just a notational thing, but what this because in those cases, let me go to the picture. Because in these cases, it's that M is recording the number of hyperplanes. And
so they might not exist. Okay.
Double, it just, yeah.
All right. That works. And then, so I guess, does anyone else have questions? Nantal, to help answer your question, the problem with the picture here for the third family is that this one is always congruence normal, right? Because it has only 8 hyperplanes. And so that's part of the first group.
Oh,
Yeah.
I see. So I would like to see one where we have 17.
Right.
Yeah.
So for that one, we'd have to draw the octagon.
Oh, and then that might have some outside region. I see. That's interesting.
Are there any other questions? I think that answers your question, kind of, Nantal, right?
Kinda, yes.
Because I assume you don't have a picture. I don't remember seeing a picture of that, one of those hyperplane arrangements in your slides, right?
Not in the slides. I could try to. I could bring up a picture. Might take just a minute.
That's okay. I guess we can save that for after if Nantel wants to see it. For now, I guess I don't see any other questions. So we'll thank the speaker again.